just coming here made me realize how much better an in-person conference still is. It doesn't even compare. So it's been really great being here again.
Okay, testing. This talk is going to be about testing. Good morning, everyone. How are you all today? Just past the midweek, halfway through point. If the prices in the bar haven't been putting you off, maybe some of you had a few late nights already. So I'm here to blow the cobwebs away with a session on testing on the Back to Basics track this morning. So good to see you all here. Now, before we get started, just a little bit of inside baseball. They give us these slides to put in right at the start so that we've got consistency with all the rows. So you put that one up at the start, then if you've got your own title slide, you can go to that afterwards. So I'm going to do that now. So here's mine. Now I'm doing this just to highlight the elements of this slide. So just to remind you, this is the Back to Basics track. Which means it's sort of no frills. We're not going to go too deep on any advanced stuff. I might hint at some things beyond the basics, but we're going to be looking at the fundamentals this morning. And it's going to be the fundamentals of testing. Various forms, but we're going to focus mostly on unit testing. And we'll talk about some other forms of testing as well. And then there's me. I'm Phil Nash. Some of you may know me from previous talks here, or from being the original author of the C++ test framework, Catch, now Catch 2. Anybody use Catch or Catch 2 here? A few people, so you'll see a bit of it today. I'll show a couple of test frameworks. But I'm also a developer advocate at Sonar, hence this t-shirt. So we do static analysis tools in the same sort of wheelhouse as testing. It's all about code quality, clean code, that sort of thing. So worth mentioning that. But I'm not going to talk about that anymore in this session. Feel free to come up and talk to me about it afterwards if you want to. You can also reach me on, well, I'm not very active on X these days, but you can probably reach me there. Slightly more active on Mastodon, not that much, but there's other ways to reach me as well. Do feel free to reach out if you've got any more questions after this. Let's get started then. And since it is Back to Basics, let's start really with the basics, the fundamentals, and ask this question, what even is a test? When we talk about testing, what do we actually mean? And there is a reason I'm going to pick at this thread. I want to give my definition of what a test is. So I think it'll be useful for some of the things we'll go on to. This might seem a little bit basic to start with. But basically we start with an operation, usually calling a function, member function, accessing a variable, that sort of thing. That's the operation. There may be input values going into that. If it's a function, the arguments. If it's a member function, there may also be some additional state in the class. That's all part of the input values. Even global variables, they're considered part of the input values. Setting aside for the moment any judgment about whether that's a good idea, they are part of the input values. And then we have one or more expected output values, the return value of a function, the state you put a class into or an object into, even, again, setting a global variable. That's the expected output. Okay, hopefully nothing too surprising so far. And we can map that over a typical test framework assertion. So here, assert EQ, assert equals is the macro. But then our operation is a call to this function called add. We give it a couple of arguments, so they're our input values. And then we have our expected output value, the thing we're testing against, as the second argument to the macro. Again, nothing terribly surprising yet. But now we've got this sort of template for what a test really is. We can say, well, that applies to other things as well. For example, manual testing. You run your program. That's your operation. You maybe supply some input, maybe typing something in on the command line, clicking something in a GUI, whatever it is, that's your input. You do manually. And then you expect it to show you some specific output, produce some result that you will manually verify. These are expected output values. Same template, satisfies that same definition. Again, not too surprising. But what about this one? The operation could be that you invoke your compiler, and you give it all your source code, that's your input value, And then if it compiles, well, that's your expected output. It passed the test. You can consider the compiler a form of test framework as well. And if you really think about it as a thought experiment separately, you can think of other things that match this definition of a test. And a lot of the things that we learn about testing can apply to these different things, and some of them could be surprising. So sometimes it's worth revisiting those assumptions, shake them up a bit. There are many types of testing. So we're going to focus mostly on unit testing today, but I did put a slide together a few years ago and I've reproduced it here. Right, I did some research, tried to find all the different types of testing I could, put them all on one slide. Don't worry, you're not meant to read all the names. There's a lot there, and since then I've discovered a few more. I haven't even put them on there yet. The point of this is you're not meant to go and learn all of these forms of testing. You don't need to. There's some very specialized forms there. Really, in my experience, there's 3 categories of testing that really matter for most of everyday programming. And they can be found in these 3 examples from this list, which I'll zoom in on so you can actually read them. So we've got unit tests. So we're going to focus on this. And this is where, these are the low-level tests that we write in our code, exercising other little bits of code, ideally in isolation. We'll talk a bit about that later. And we want to have most of our tests be at this level. Then we have integration tests, which are somewhat similar. They may sort of exercise more parts of your system, have more things working together, but they look very similar to unit tests. And the system tests, at the top there, they're more like the end-to-end tests. Again, these are categories of tests, not specific tests. So UI testing, acceptance testing, manual testing, all of those things, even fuzz testing, throw loads of things in there. But they exercise your whole system end-to-end, and very valuable, but also very difficult to work with, to automate, and so on. Now, the reason I've illustrated them this way is because they form what's often called the testing pyramid. And the idea behind the testing pyramid is that unit tests at the bottom, the big one, are where you should be spending most of your effort, most of your tests, according to the testing pyramid idea. Most of your tests should be unit tests, often by far, because you get the most value out of those. When something goes wrong, you know exactly which bit of code caused that failure. They should be fast to run, cheap to run, easy to write. You know, everything's good, but they can't cover everything. In particular, integrations between components at a high level, well, that's what the integration tests are for. Again, they look very similar to unit tests, can be deceptive. There's even like a very thin line between them sometimes. But it is worth keeping those separate. You'll want integration tests, but not as many. Because, well, we'll come on to exactly why in a bit. But they have a bit more of a cost to them. And then similarly with system tests, as I've already said, they're quite hard to work with, to maintain. They can often be very long running. I hear reports of people that to run the whole test suite, it can take days or weeks to run. Not something you want to run after every change. So that's the idea behind the testing pyramid, and that's why we put so much emphasis on unit tests. It's not that the other forms of tests are not important. It's just that this is where we want to give most of our attention and best practice. So let's drill into that a bit more and look at the unit test level. And I'll reframe that question. What is a unit test? Well, I usually defer to microfeathers on this. We're going to hear a lot about microfeathers today. Who's heard of microfeathers before? Maybe a couple of people. Definitely worth looking him up. He's written many books, articles, and so on. And a lot of the law around unit testing comes from microfeathers. This is no exception. Now here's a definition of unit testing, or rather a set of unit testing rules that he came up with. And it's interesting because it's defined by what they're not. He says, a test is not a unit test if it does any of these things. It talks to a database, communicates across the network, touches the file system. If it can't run at the same time as any of your other unit tests, so there's some sort of dependency there, or you have to do special things in your environment, like editing config files to run them. If any of those things are true, according to Michael Feathers, not a unit test. Doesn't matter what level it's at, how you write it. If any of those things apply, not a unit test. Now, this is maybe not the classical definition of a unit test, where we try to define what a unit is. Is it a function or a class or something? And that's still approximately true, but this is a more pragmatic definition that really gets at the reason why we want to keep these things separate. Now, the interesting thing is all of those things that he says, this is not a unit test, these are all things that will make our tests unreliable, unpredictable, and slow. So, by contrast, a unit test should be fast, reliable, and consistent. So really that's his unit testing rules. Now he goes on, says a bit more. Because after saying that, you might think, oh, I shouldn't do those things. But no, he said, tests that do these things aren't bad, and often they're worth writing. And they can even be written in a unit test harness. So this is where some of the confusion lies. You'll often see unit tests, and really what we're talking about now are integration tests, very often. Running side by side, they look very similar in the same test framework. But they're serving different roles, and it's really important to keep those things separate. And here's the reason why. So he says, however, it is important to be able to separate them from true unit tests so that we can keep a set of tests that we can run fast whenever we make our changes. So really here, emphasize the speed of running your unit test as being the primary principle. Determinism, reproducibility, reliability, they're all important aspects of that. But if you can't run all of your unit tests quickly, they're not serving the purpose of a unit test, according to Michael Feathers. And we'll dig into it a bit more later. Going to leave that there for the moment, other than to just say, this is exactly why unit tests are at the bottom of the testing pyramid, why most of your tests should be that way, because you want to run as many tests as possible every time you make a change without it interrupting your flow. That should be quick, fast, and easy. All right, let's switch gears a little bit for a moment. We'll come back to this topic. I want to talk a bit about test frameworks. So there are many test frameworks. What should we use them at all? Which ones? How do we compare them? Let's talk a little bit about that. Let's first ask the question, should we use a test framework at all? And if so, why? Let's take a look at a code example. Keep this really, really simple, trivial. Imagine you've got a function that adds two numbers together. Okay, I won't even bother showing the implementation, at least not yet. If we've got this function and we want to write a test for it, how would we do that? Well, without any additional dependencies, we can use CassErt. It's in the standard library, even the C standard library. We know it. It's pretty straightforward. We know exactly how it works. Just write the assert macro, make a call to our add function, and compare it against our expected result. We've got those three parts from that template of what is a test there. That was the example we even saw earlier. Okay. What happens if this test fails? So let's actually introduce an implementation. We'll put a bug in there just to see it fail. Now, if we run this, what will we expect to see? Well, when I put this slide together and I ran it on my machine, this was the output that I got. Now, that output is very implementation specific. It will vary. The things you get on there will vary. But this is actually not bad. So we can see, first of all, we've got the expression you wrote originally, the add 1 and 2 is equal to 3. It's captured there in the output. In my version, we also get the name of the function. This is probably the bit that's most implementation specific. This will vary a lot. But if you do get it, that's really useful because you could put your tests in a function and give the function a name like a test case. And you'll see it in the output. So starting to approximate what a test framework does. Unfortunately, not all compilers will give you that. You will almost always get the file and line number, though. And if you're running this in an IDE, you can click on that and it'll take you right to the line. You get a lot of output. It's actually pretty good. So again, well, why do we need test frameworks? Doesn't CassErt do it all? Well, let's weigh up the pros and cons. I think it's important to see what the pros are of just using CassErt. So no dependencies. That's a really big one. If you're just bootstrapping something, you just want to get something tested quickly, straight away, you can reach for C assert and it will actually do quite a good job. Without any dependencies, you do get some useful output, file and line number, the original expression, maybe even the function name it was in. And it's a natural familiar syntax that we all know. We don't have to rephrase our expressions in some macro syntax. We just use what we already know. That's pretty good. Of course, there are some downsides. So let's go into those, at least some of them. So first of all, while the feedback's not bad, it's not that great either. We could do a lot better. And very often, you'll be running all of your tests, say, on a build server, and you'll get a failure overnight, and the next day you come in and you'll see the failure, and you've just got to trace from the output what actually went wrong. So you want as rich feedback and clear feedback as possible. So the more we can get, the better. And in particular, we don't get the breakdown of that expression. We know that add 1 and 2 didn't return 3, but what did it return? We didn't get that. That's really useful. We're going to get output to the console. We can redirect it to a file, but it's basically just text-gen output in an implementation-defined, non-structured format. We often want something that we can feed into some other reporting tool, or at least visually present it nicely, and especially if we've got more rich feedback. So that's the limitation. We don't have test names. We may be able to fake the function name. That's not reliable. We certainly don't have the ability to group them into suites. You could add a layer to do that, but at that point, you're already on your way to writing a test framework. You may as well use one. And it aborts on the first failure. The whole program just terminates. The test framework will usually abort the current test case on failure, but then run the rest of the test cases. So that can be valuable as well, especially, again, if you're running on a build server. There are other pros and cons, but I think this should be enough to give you a taste of, well, it's worth looking and investing in a test framework. So which one do we pick? So you might go to Wikipedia, which has a page list of unit testing frameworks. And there's a section on there specific to C++, and you can scroll through there, and I hope you're taking notes. Because last I counted, I updated this a few days ago, there were 84 C++ test frameworks just on that Wikipedia page alone. I haven't tried all of them. And that's the thing, like with the different forms of testing, there's too many. We can't try all of them. So what I'm going to do is just take you from a very high level through some of them to give you an idea of the field, what's popular, what's historically relevant, what you might see out there. Starting with CPP unit. Now this is more of historical interest. You will still see this today in production because it was around 10, 20 years ago. This was the first unit testing framework for C++ of the modern mold. And it was really a port of JUnit from the Java world, and it sort of lost all the things that made JUnit good, specific to Java, didn't really pick up enough of what made C++ good, so it was like the worst of both worlds. But it was a good start. It was actually written by Michael Feathers, who we met earlier. And at some point, he got fed up with it. It was too complex, didn't do what everyone wanted. So he then wrote CPP Unit Lite, more cutback that you can build your own things on top of. You won't really see much of CPP Unit Lite today, so I'm not going to dwell on that. Again, just for historical purposes. And just to emphasize that, yeah, there are different test frameworks with different trade-offs, and you need to have an idea of what it is that's important to you, even if you wrote them, apparently. The first one that came along, I think, that really sort of captured the spirit of C++ was boost test. Unfortunately, it was the spirit of C++ 98 at the time. So it picked up all the idiomatic verbosity and doing everything in a really explicit way. It's got a bit better in recent times. You'll still see boost tests used quite a bit. It's still one of the popular ones. I don't think it's the best one these days. The big one now, of course, is Google Test. So by far the most popular test framework in C++. So if you see Google Test, then you're pretty safe, I think. It's a good framework. It still suffers a little bit, I think, from that sort of port of JUnit heritage, but it does capture a lot more of what C++ gives you as well. It's well maintained, it's got lots of features, lots of people know it, so you can't go too far wrong. Of course, that's never good enough for some people, so I wrote my own, 14 years ago now. Originally Catch, then became Catch 2. According to some surveys, and I'll show you one in a minute, it's now the second most popular test framework after Google Test. So it is worth knowing Catch, and it does a few things differently, and a few other frameworks have sort of followed these trends. We'll talk a bit more about Catch later, because I'm going to show you some examples using it. One of those frameworks that follows the Catch trend is doctest. And the main difference with doctest is it really prioritizes performance, both compile times and run times. So if you've been using Catch and you like it, but you're finding that it's not fast enough for you, give doctest a try. It's not as fully featured, but if speed is your priority, then it's definitely worth a look. Another one I'm going to throw in, and I haven't actually checked recently what the status of this is. It used to be called Boost Experimental UT. Now it's just become UT for unit testing, from Chris Jusiak. The principle behind this was, I said, the earlier frameworks were basically ports of JUnit and the early C++ style. This is a big reset. This is like, what can we do in a unit test framework today with C++ 20 features and just go all in on that? And he even manages to pull it off without any macros. So at least from an academic perspective, this is really interesting. And it may actually be a good framework as well, but I haven't tried it recently. So I throw that in there more as an aside. There are others. I've seen a couple come along in the last year or two that claim to be similar to Catch and doctest, but maybe even faster or even more modern. It's a rapidly expanding area. I'll just very quickly show you the JetBrains Eco developer ecosystem report. This was from 2020, because they changed the formatting after that, and it's a bit harder to read, but you can see Google Test, by far the most popular test framework, nearly as popular as writing no tests at all. Which unfortunately in 2020, according to the survey, was 34% people, third of people surveyed didn't write tests at all. And then another third used Google Test. You can see Catch there in second place. I don't know if you can read it very clearly, but Boost Test here was the next one down, then CppUnit, then doctest. So many of the ones that I mentioned, they're all players. This was the 2022 report, very similar. Actually, less people don't write tests, so that's a positive trend, if that's really reflective. More people are writing tests now. And I like to think that a lot of that's because of all these modern frameworks, including Catch, making it easier to get into testing. Traditionally, it was very hard. So if you're writing tests at all, you're already in the top 74% of C++ developers. How about that? All right, let's get to some code and actually look at something a bit more real world. Well, the trouble with real world code is it's often too complex to show in a slide, so you always have to simplify it. So I've picked an example from a real world report. You may recall some years ago now, there was this incident in the JavaScript world where this library that left pads strings got pulled by the author, and half the internet stopped working because apparently they all depended on it. And we're all thinking, why do you need a library? Everyone depends on this library for something so simple. Just write it yourself. So let's do that. We write left pad in C++, and we write some tests for it. So we're not actually going to look at the implementation, because we're just going to look at the testing. Hopefully you can read that. Try to fit it onto one line. That's our signature that we're going to be testing against. So given that, we want to start writing a test. I'm going to start with Catch. So you include Catch, and then everything goes in a test case. So this is the outer container for your tests. And you can give it a name. We call it left pad for now. We might revisit that. And then your actual test, your assertions go inside there. If you've used any test frameworks before, this should all be quite familiar so far. Maybe the one difference, one of the things Catch does differently is the test case name is a string. You may have seen in other frameworks, you have to write it as an identifier. In fact, let's look at that. Let's put it side by side with Google test. So the equivalent so far, G-test. So left pad with an underscore, because it's an identifier. We've also got this empty thing after it. It's because in Google test, the first parameter is the name of a test fixture. And that fixture can have multiple test cases. So the second name is the name of the test case. We'll look at how that stacks up in a moment. But otherwise, these are equivalent. Now, so we might revisit the name. We'll talk more about naming later, but I think we can do better than just left pad. This is a very common pattern. You think, oh, I'm testing left pad, let's just call it left pad. But it doesn't really tell you why. It doesn't tell you what the tests are meant to be doing. And sometimes you don't even know that until you've written them. So do go back and revisit test names if they no longer reflect what you're testing. But we might write it something like this. Left pad, pad strings to a minimum length. It tells you a bit more about your expectation. And now we can see more clearly the difference between the different test naming approaches. All right, let's actually write some tests then. So we use these assertion macros. Again, keeping Google test and catch side by side while we can. That we'll reach a limit of scalability in a minute. In catch, the standard assertion macro is require. And then that works very much like CassErt. You just write a normal expression in there. Whereas Google test has the more classic approach where you have different macros for different comparison operators. So assert EQ for the equals operator. And then you have to supply the left-hand side and the right-hand side as separate arguments. And the reason you do that is, as we said earlier, if this fails, you want to see what the result of left pad actually gave you, not just what it didn't equal. And so that makes it easy to do. Catch still achieves that, but it uses expression templates to break the expression down for you, which means you get that slightly nicer syntax. But they're still equivalent. Then the other thing to notice here is we've changed that second argument in the Google test case, because now we've got something more specific that we're doing. We're saying an empty string with 0 padding. So we can do the equivalent in catch, it's just a little bit different. So let's add another test and see where that takes us. Because it's not actually about empty strings, it's more about the 0 padding that's important. These two things are quite similar. So now we're calling left pad with different strings, including the empty string, but 0 padding, and we're seeing that it returns the original string. So in the Google test case, we've given the test name as not padded when minimum length is less than the input string length. And you can maybe come up with a better name than that. But it's describing what it is the test is doing in natural language, right alongside the test doing in code. I said we can do the same thing in catch. Catch has something called sections. These work a little bit differently. And again, you can just use free-form strings. You're just grouping your test together that way. And in a moment, we'll see how that scales differently. But so far, these are pretty equivalent. OK, well, we're not going to go through these one by one, but I'm going to fill out at least a screen full of tests against left pad. So you can see we've got multiple tests for that. This is Google test. That same first argument, so the same test fixture. You can think of this like a group of tests with something common to them. They're all, left pad strings to a minimum length. First one is the one we just saw, not padded when min length is less than input string length. We've got 2 assertions in there. Second one, padded when min length is equal to the input string length. And then when the minimum length is greater than the input string length. And finally, when we use a custom character for the padding. So these are all related but different tests. So they've got different test cases with different names. And you might be tempted to stick these all in a single test. And you can do that, but this is just more descriptive. It gives you better feedback if any of them fails. And they're grouped according to their property, which can help you when you're thinking about, well, what things do I need to test? What sort of properties am I testing here? And we might even touch briefly on property-based testing later, which is an extension to this idea. But this is an important thing. It can be quite tricky to, when you're there at the code base, to think, what is the next test I should write? So thinking at this level helps you to do that. So let's look at the equivalent in catch. So Single test case, that's our group, our test fixture, if you like. And then the sections are playing the role of the test case in Google Test. And again, we can use free-form strings for that. And now it's actually easier to notice that the first two sections, when padding is less than the string length and when padding is equal to the string length, the tests are almost identical. The result is the same. We might be tempted to just combine that into a when padding is less than or equal to string length. But that's only because we're expecting the result to be the same. But if it wasn't, if it failed in one case but not the other, then it becomes harder to see what the problem was. So separating them out this way is valuable. Again, it's all about thinking, what's the feedback I'm going to get from this test if it fails? Not just, how can I test it? So you can see we're starting to touch on testing practices, best practices maybe, to get the best out of our tests. So let's dig into that a little bit more and talk more generally about testing best practices. I'm not going to cover all of the principles I would normally talk about. I do a 2-day class on TDD, and I go into this in a lot more. But I'm going to try to bring you the highlights, because even now there's quite a few. I'm going to focus, first of all, on unit tests, and then we'll talk a little bit about testing in general. Here's a set I want to talk about. I brought them all up together because it looks like a lot, but actually when you break it down, it's not so bad. But the first 4 are actually really covered by what Michael Feathers already said earlier about tests being able to run fast, that most important one. And a part of that was being deterministic and reproducible, so not depending on the order of the test or any of your environment. And as a result, they should be self-contained and isolated. So they're all sort of part of the same thing, really. The isolated part is interesting because you can take that further, and you can try to isolate code down as small as possible. We're not going to talk about mocking today, but if you've come across mocking before, that's in the area. There are some dangers there as well, but we're not going to get onto that today. So isolated as possible, I would say. Consistent and reliable. We don't allow tests to work most of the time and sometimes fail or give different results. They have to be reliable. Be obvious and self-documenting. This is, I think, subtle but really important. If our test code is complex to read, like a lot of our production code is, then how are you going to be able to say, well, I can see that that's correct? Because you're relying on the test to actually not prove the correctness, but at least check the correctness of your code. But if you can't tell that the test is correct just by looking at it, it's much less valuable. And it's much harder to maintain and for other people to see what's going on. The same does apply to normal code as well. But I think with test code, we have the opportunity to be much simpler and more obvious and direct. And the temptation sometimes can be to have too many helper functions and elaborate class hierarchies just to help us simplify the test, but actually we're making it more complex. I've done a whole talk on that. Keep in mind that it should be self-documenting as well. Again, if you've got to read some other document to understand why the tests are written the way they are, you'd probably be doing something wrong. As well as self-documenting, there can also be a form of documentation for the code under test, and we'll look at that a bit later as well. They should be focused on one thing at a time. You may have heard of the single assert rule. This is related to that. We'll pick that apart in a minute. Again, there's some nuances. But again, if you're trying to do too many things at once, then if it fails, it's going to be unclear what the cause was. And finally, and maybe this is the most controversial one on the list, always test via the public interface. And what I mean by that is, it's very tempting to write lots of tests against your implementation details. I think, well, I've got this implementation, I need to test for it. But if that implementation is not really visible or observable through your public interface, then it can change for reasons that are unrelated to your ultimate requirements. And that makes the test really brittle. It can also make the test hard to write. And it can mean you can end up changing the interface of your code purely for testing purposes. And it can damage the code. There are some cases where you do need to do this, and I usually talk about non-functional requirements. So a good example would be if you're writing a class that's basically a smart pointer, reference counted smart pointer, and you want to test that the reference counts a certain value at a particular time. It's part of the non-functional requirements, but it's not part of the public interface, or at least it shouldn't be. So occasionally, you might need to poke this hole into your encapsulation. And there are some techniques to do that. I'm not going to talk about them now, but they should be very, very rare. But they do come up. Most of the time, people just want to test implementation. And probably the biggest workaround for that is to pull some of those implementation details out into their own class or component with its own public interface that you can then test. But there is a caveat here. It's still implementation detail, at least at this point. It may become something more later. But if it remains an implementation detail, it's still true that that implementation detail can change for reasons other than the overall behavior of your system. And that makes those tests more brittle. So it's worth keeping them separate. They can still be valuable, especially when you're first writing it. And sometimes it will be like a stepping stone. You write the implementation, you get the test around that. Then the code that uses it has their own tests, and ultimately that implementation detail is tested indirectly, and you don't need the low-level test anymore. So the important thing here is to know when you're doing this, when you're testing implementation versus public interface, because it's the specified behavior that's important here. Okay, for all tests, they're not just unit tests. A few best practice principles. We've already touched on this one. Your tests should always be well named. They should describe what it is that you're testing in a way that can be obvious out of context. Failure on a build server, for example. And related to that, they should provide clear and useful feedback. In the event of a failure, sometimes there's some contextual information that you also need to capture and print out. And most test frameworks will give you the ability to capture variables that will only print out in the event of a failure. Certainly Catch does, I think Google Test does. Most do. Do make use of those, because that context can be really important as well as part of that useful feedback. I know I'm repeating myself a lot, but sounds obvious. These are the things I see not done very often. Next one's a bit odd, at least at first. Have a clear reason why you're writing the test in the first place. Usually we feel we're not writing enough tests, we should write more. But don't write tests unless there's a clear reason for writing that test. Just feeling like you need to write more, or somebody else is telling you write more tests. If there's not a purpose for it, it's probably wasting your time writing it. It's wasting runtime every time you run it, and it may end up being brittle. So make sure you understand what it is you're getting out of the test. And sometimes you can end up with less tests than you thought you needed just by applying this principle. Next one is a bigger topic that I'm just going to scratch the surface on again. But your test should have low cyclomatic complexity. This is related to a point I made on the previous slide about the test being sort of obvious and self-documenting. By cyclomatic complexity, really we're just talking about control flow, if, for, switch, those sort of things. In practice, this is actually true in general in your code. Don't have too much cyclomatic complexity. Just enough, I think. The reason it's worth calling out specifically for test code is because you should usually aim for this to be 0. You shouldn't have any ifs, any fors, any do-whiles in your test code. There are some cases where you do need it, and there are often limitations of the test framework. For example, if you're writing a for loop, you're probably trying to test properties rather than specific examples. And maybe you just need a feature in the test framework to do that. Either a fully fledged property-based testing framework, which has rich tools there, but Catch has generators, which will get you most of the way there. So if you find yourself writing at least a for loop, ask yourself why. Is there a feature in the framework that will give you the same result? Again, if statements, Sometimes there's reasons why, but again, often can be replaced by features in the test framework. We don't have time to get too much into those, but that's the point I wanted to make. Aim for 0 cyclomatic complexity. At the minimum, low cyclomatic complexity. And it's all part of that, keeping things simple and obvious so you can look at it and see exactly what it's doing. Okay, we're going to have to move on quickly. So I want to get back to some more code and look at another example where we have something a bit more stateful to get our teeth into. Previous one was just functions. So now we have a most recently used list. Thought it was an interesting example that I borrowed from Kevin Henney, because not many other people use this one. So most recently used list sort of works a bit like a stack, but if you put an entry on there that's already there, it just removes the previous instance. So you don't get duplicates, it just goes to the top. So think of most recently used files in an IDE or browser or something. So that's what we're working with here. We won't actually get into what makes it interesting in the test. We've got 2 sections here, so it's not complete. Just going to stick with catch for now. Too much code to do the side-by-side. The first problem here, we alluded to this one earlier actually, is the test name. Again, it's just stating what the thing you're testing is, not why you're testing it, not what its purpose is. So I think we can do better than that. Already explained what a most recently used list is. Let's just write that as the test name. Most recently used list acts like a stack, duplicate entries, replace existing ones. Now you've got some context that if you get a test failure, you can say, that's not fulfilling that part of it. Now we've got section names as well. They're not too bad. They state your expectations. And section names in Catch or the test names in Google Test, generally they should state expectations, and then the test case or test fixture should give you the contextual description as a general principle. And this will give you the richest feedback, again, in the case of a failure. Now, we will start off by creating our most recently used list. And it might seem obvious to do that in this case. In some cases, not so much. That in order for your test cases to be reproducible and deterministic, as we said earlier, it means we need to set up all of our state from scratch every time. We can't have it set up somewhere else, and then we use it here, and then something else uses it. Everything set up from scratch every time, self-contained. And we've even got a pattern that we tend to follow. You may have heard arrange, act, assert. So the first phase, we just set up our initial state. Again, everything should be here. There are some cases, like maybe if you're working with some environment that you don't control and you had to set things up globally, yeah, do that if you need to. But the thing you're actually testing, you need to be able to set it up from scratch and leave the system in the same state at the end every time. So we arrange it at the start. Then we perform an action, the act stage. But we don't always do this. We might test that base state like we did in the first section. The empty list, we got tests for that. That's fine. But usually there's some action that's going to put it into a different state. And then we can assert on that new state. Again, nothing that complex, all pretty straightforward. But it's just worth having these sort of things in mind so you think, that's how I structure my tests. I need to create everything every time. Notice the word assert there is singular. There's actually 2 assertion macros. I mentioned earlier the single assert rule. You may have heard that before. So what's going on here? I like to call it the single logical assert. So what we're really saying is the empty list, that's a single state that we want to assert. There might be multiple ways to assert that or part of it. So you might actually need more than one physical assert statement, but it's a single logical assert, and that's fine. That's not a violation of the single assert rule. What the single assert rule is trying to protect you from is this sort of thing, where you say, okay, I'm in the empty state, I'm going to assert on that. Now I'm going to perform the action, and now I'm going to assert on something different. These are now multiple asserts, and you've got like a dependency between them. And that starts to, well, it makes the test more complex. It makes it less obvious what's happened if it fails. And it can just make it more brittle, because you can't change the earlier states without changing the later state anymore. So the single assert rule says don't do this. The way we did it in separate sections or separate test cases in Google Test is how we do that. And that also drops out of arrange, act, assert, because this is arrange, assert, act, assert, not the same pattern. So really those two things are basically the same practice. So there, I think the key best practices for testing that I wanted to get to. There are others, but we don't have time to get into them now, because I've only got 14 minutes left and I've got some big sections to come, so let's get into those. Let's look at some challenges and pitfalls of testing. A lot of people say, oh yeah, I tried testing and I had all these problems and it wasn't worth it. They gave up. But actually at this point, I think we already have the answers to the challenges I'm going to present. Again, it's not going to be a complete list, but these are the most common things that I hear about. Maybe you've got flaky tests, sometimes called flickering tests. So tests that will maybe pass most of the time and fail sometimes. And they pass often enough that we sort of tolerate them because, yeah, they're valuable, but they're not that valuable if they're failing. Then we should have zero tolerance for flaky unit tests. If it's not a unit test, if it's something that depends on something in the environment, that's probably why they're flaky, and we have to make a decision if they're valuable. But for unit tests, we should have zero tolerance. If something becomes flickering, that's a problem you need to look into. And if you're not, why are you even testing? So zero tolerance for flaky tests, unit tests. Low tolerance the rest of the time. Even if, yeah, you've got some unreliable environment, there's often ways that you can mitigate that. Like maybe check something up front and don't perform the test if it's not in that state. Most test frameworks will have features that will run a test, and if it fails, not fail the whole test run, but still report the failure, so you can keep track of it. So use features like that if you need to. But don't tolerate them in unit tests, ever. Slow tests, well, if our unit test should run fast, we should never hit this problem. And if we do, well, it's probably because we violated one of those principles that Michael Heathers gave us. And maybe we got some tests that we thought were unit tests, but actually they're more integration tests. I often like to think of integration tests as being the unit tests that didn't make it. They look like unit tests, but they've just got some dependencies you didn't quite want, or they run too slowly or something. Well, we're not about to run them, but not as part of your default run that you run after every change. That's unit tests role. Make sure you keep them separate, you can run them separately. So don't tolerate slow unit tests. Again, zero tolerance there. It may just mean you migrate them to integration tests. But even integration tests shouldn't run slowly. You should be able to run them frequently, just not necessarily every time. So this is something we need to keep on top of. There's lots of other techniques, but most of them are the ones we've already talked about. Brittle tests, we talked a little bit about that. Most often, I find that brittle tests that break easily. You make a change, everything's fine, but the tests break. What's the point in testing? It's just holding me back. Well, it's probably because you're testing against the implementation. The number one cause in my experience. There are other reasons sometimes. That's the number one cause. So the solution is either don't do that, or if you need to, recognize that you're doing that, treat them differently. Don't be afraid to delete tests if they serve their purpose. If they're being tested indirectly somewhere else because it's an implementation detail, that's okay. You might need to consider on a case-by-case basis, is it worth rewriting some new tests? Probably not, but in my experience, that's usually the solution. Or if the tests are hard to write in the first place, and this is typically true if you're coming in an existing code base and you're trying to put tests in, tests can be really hard to write. Well, ironically, this is a good thing, because this is a test telling you something about the design of the code. And especially if you are writing fresh new code and your tests are hard to write, well, that's giving you early feedback that there's a problem with the design. On the face of it, it's not a testable design. But in practice, what that means is you haven't got well-factored code, good separation of concerns, cohesion, all of these principles. We'll talk a little bit about design principles if we have time in a moment. The test will tell you, they'll shine a light on those problem areas in your design and give you a chance to do something about them. It's a bigger problem if you're working with legacy code. That's a big topic we're not going to go into today. There are other techniques there as well. But where possible, if tests are hard to write, follow up on that and look at why they're hard to write and whether you can change something to make them easier. Right. So we talked a bit about how you get started writing tests, different test frameworks, some of the best practices. Where do we go from here? Especially as we're going to be finishing in 10 minutes. What are you going to do next? So here's my proposal. First of all, get comfortable with those best practices. They sound simple when I'm saying them from up here, and you're probably already aware of most of them. Actually putting them into practice is a different thing. Don't expect to walk out of here and just magically be able to do it all. It does take practice, experience. Work on that to begin with. Also become familiar with those design principles. We hinted at a moment ago, we might talk about it in a minute, but particularly separation of concerns, loose coupling. They're the things that are going to make testing easier and give you a better design that is more changeable over time, easier to change. So make sure you're familiar with the design principles that will give you that. As we said just now, pay attention when testing is harder, because that's going to highlight those areas that you need to pay attention to. And then, if you've done all those things, it's a great time to consider test-driven development to take you to the next level. Now, I think we've just got time to very briefly give an overview of TDD, a taster, really. So I'll do a two-day course on it, so we're not going to get you to be TDD experts. But if you've heard of TDD, you probably think, yeah, it's about writing the tests before you write the code. And that's a big part of it, but it's not all of it. It's all about what we call the TDD cycle, which usually looks something like this, sometimes also called the red-green refactor cycle, after the names of certainly the red and the green sections. And apologies if you have any difficulty distinguishing colors. Doesn't matter, it's just a traffic light metaphor. The point is, this is actually pretty simple. Fits on a slide. I can explain it in a couple of minutes. Mastering it takes a lot longer. It's the discipline of it and the nuances that are tricky. But here's the main principles. We always start by writing a failing test. So it has to be failing. If you write a test and it immediately passes, it's not part of the TDD cycle. Now, think back to what we said earlier about what a test actually is. It could be the compiler failing. So you can make a call to a function that doesn't exist yet. You see it failing in the compiler. That's your first red. You've written a failing test. To make that pass, to go to the green step, we have to write just the code to make the test pass. So if that's a missing function, we write the function, we stub it out. We're not writing an implementation because we want just the code to make the test pass. Return a dummy value if you need to. And if you're testing some implementation, then you write the minimal code to make that test pass. We're not worried at this stage about writing clean, well-factored code. It's ironic, but that's what we want to end up with, but we're not doing it at this stage. We just want to get to green as quickly as possible, hence the word just in there being highlighted. Because we have a separate section, the refactor step, where we do clean up the code. We don't do that until we got to green. When we're at green, all the tests are passing, now we can refactor. And we can do so knowing that if we're doing pure TDD at least, if we break anything, the testers are going to immediately tell us. So we do that safely. It gives you a lot of freedom. There's lots of other consequences that flow from this, which we don't have time to get into here, including even how you think about code. how you think about approaching code. And we have this extra step where we can check, are we done? Do we have another test to write? Seems obvious, but when you're there at the code face, sometimes you can get carried away and write stuff you didn't need to. It happens. So it's nice to have a separate step for that. That's the TDD cycle. And at the green step, if it's hard to make your test pass, or it's hard to write the test in the first place, remember that's the test telling you something. That will lead to a better design, and the refactor step is where that magic happens. So I think that's all we have time to cover on TDD. And so it's just a taster, because I did want to talk a little bit about design principles. We talked about loose coupling, separation of concerns. You may recognize those as part of something called the solid principles. Single responsibility principle being the first one. Likely you've heard of the solid principles, but don't remember all of them. That's fine. I ask experts this from time to time, and they can't always recite them all. I'm not going to go into these in detail, mostly because they have been criticized lately, including by myself, as being not that compatible with modern C++, or even with modern design thinking in general. And there's something to that, but there's also a lot there to learn. And I want to draw your attention particularly to, well, this talk in particular, but a whole series of talks from Klaus Eagleberger, who's here this week, but this one was from 2020, where he takes the solid principles and he completely updates them for modern C++, makes them entirely relevant. Definitely worth looking into. Lots of really good stuff there. The connection here with testing is that these principles are all things that will help you to make your code more testable and lead you to a better design in the process that is more maintainable and evolvable over time, which is really what we wanted. I've done some talks on a similar subject, mostly focusing on simplicity, which I think underpins all of this, and what that really means. Again, I'm not going to get into that in detail right now, because I want to get to my final slide, where I have a link to, on my website, levelofinteraction.com/refs/testing.html, has a load of references. Well, there's a few there at the moment, I'll add some more later, to things like Klaus's talks, my talk, Michael Feather's blog post, all of those things, they're all in one place. So I'll leave you to grab that, where to find me, but that is me. So thank you very much for coming. Do you have a couple of minutes if you've got questions? Yeah.
So one of the Michael Feather's rules for unit tests was that it doesn't touch the file system. If you've got something that is inherently kind of tied to the file system, is it that you say, okay, this just isn't a unit test, it's an integration test? Is it more of a, you mock out the file system? Is it, you can touch the file system, just not at runtime? Or do we just say, we don't care about that rule this time?
The obvious answer is it depends. Yeah, very often you can mock it out, at least for unit testing purposes, but you'll still need integration tests. The file system one is the one that I'm probably more lax on than Michael Feather's. So I'll often have just support code in separate files, like a JSON file or something. It's always there. I consider it almost like part of the executable. You could bake it into the executable. It's just unnecessarily difficult. So I'll do that. But if it's testing the file system is what you're actually doing, then yeah, you're going to have to touch the file system at that point, and maybe you even consider those unit tests. But the point behind all of Michael Feather's principles was having a set of unit tests that you can run fast after every change. If it doesn't fulfill that criteria, then you're going to need to be more creative or split them up differently. So does that answer your question?
Yep, thank you.
Great, thanks. And I think one more.
I have a question about an edge case, and if you have timeouts in a function, then it would be slow by definition.
Yes.
So would you consider such tests who wait on such timeouts also as unit tests, or are they more integration tests? Or
again, by Michael Feather's definition, they wouldn't be unit tests because it's going to take too long to run. again, you have to come back to that question. Can I afford to run this after every time I make a change? And the thing I didn't say about the TDD cycle, if you're doing TDD, those cycles will often run in seconds. Like you'll go through all those steps in a few seconds. And then at each stage, you're running all of your tests. If you can't do that, then they're not serving that purpose.
Yeah.
So sometimes it can be a bit of a gray area. Is this a unit test or not? And that's when I apply Michael Feather's definition to it. But again, you can write them in a unit test framework, very much like unit tests. Just don't keep them as part of your unit test run. Have it as a separate integration test run that you run perhaps less frequently. They're still valuable.
Thanks.
Okay. And I think we are at time.
Time's over.
Just one more, then go on.
About fast execution of the tests. In principle, you have to include compile times, right? Because especially
Yes.
for test driven.
Absolutely.
But
Yeah.
what if like just parsing your header already takes a minute?
Not if you do it correctly. But I mean, yeah, it's a fair point. And that's why I mentioned doc test as being a faster to compile alternative. And there are some recently that are claiming to be faster than doc test. I haven't looked into that enough yet. Definitely, compile times are a factor. Usually it's, my code base takes an hour to compile. I can't do this. But there it's more about isolating the bits of code that you're testing and only building that in a smaller component as possible. What's the word I'm looking for? Incremental builds. We'll get you most of the way there. If the test framework itself is a problem, then you're probably not doing it right, because there are certainly with catch.
It's
There
a
are ways
header only stuff that I have to test, and it's a huge template.
Yes, but the implementation part of that only compiles into one translation unit, which you shouldn't be compiling every time. But we can take this offline if we want to dig into it a bit more. But I completely agree that compile times are an important factor. That's the takeaway. So, thank you very much.